Good afternoon and welcome to our webinar on risk management using Bayesian networks and BayesiaLab. It's a great pleasure to have you join us today. Let me start off by introducing ourselves. My name is Stefan Conradi. I'm the managing partner of Bayesian USA, and with me on the line is my colleague Stacy Blodgett, whom many of you will know from telephone conversations or product demos. So let me get straight to the point. Today's objectives, we will talk about, or we will have two major objectives. The first one being a methodological objective. We will talk about how to use Bayesian networks for managing risk. The twist to all this is that we will talk about managing risk without data. That will be the really interesting part. In terms of the substantive research objective, we will look at quantifying and mitigating the risk of speeding violations in a transport business context. So we're talking about perhaps a trucking company or a delivery service. But bear in mind, this is a kind of a toy problem. We have highly simplified the problem domain, and in an almost playful way, we will try to capture the essentials of this problem and model them. So more specifically, today's agenda is as follows. We will start talking about motivation and background. We'll talk about regulations and risk. We'll perform a qualitative risk assessment. And then there comes our central idea about a risk mitigation proposal. Then we proceed to methodologies. We will see how Bayesian networks fit into this situation, how we can use Bayesian networks for reasoning without data. And specifically in this context, we will need to talk about the Delphi method, which will be our tool, our methodology for eliciting knowledge from experts. And we have then formalized all this in the Bayesian expert knowledge elicitation environment, which you will see in practice. Then the concluding part of our presentation is a software demo. We'll build a qualitative structure representing the problem domain. We will elicit the probabilities, the quantitative part with Beaky, and then finally we will use that elicited the structure with the elicited probabilities to find an optimal policy. So I haven't rehearsed this, so I would speculate we'll need about 20 minutes for the introductory part, and that will hopefully give us about 40 minutes for the software demo. That's really where the interesting things are happening. Now, in previous webinars, we only focused on BayesiaLab, our desktop application, but as I've hinted at, today we will also talk about the Bayesian expert knowledge elicitation environment, one of our web applications. So just one thing up front real quick, and that is the slides and the recording as well as the network we produce will be available for download later today. So even if you don't catch the entire webinar, you will be able to watch it later. So today's domain, it's all about trucking, transportation, delivery services, but it's really just a proxy for any other business that deals with regulations and very often relates to how businesses have to operate kind of at the limit of regulation. What do I mean with that? Let's look at this example. Very simple. We're all very familiar with this. One law that we all deal with are speed limits. And clearly for a transportation business, that is a very, very critical limit, because obviously it constrains the speed at which they can transport goods. On the other hand, given competitive pressures, business pressures, really they need to, that is not just an upper limit for them, but it really becomes a lower limit at the same time. So if you're in transport, if you're in delivery, then really your maximum becomes your minimum. And operating as such at the limit, you're really exposed to quite a bit of risk, because depending on what jurisdiction you're in, there may be some draconian penalties for going over the speed limit. Everything from not everything is draconian. Perhaps you'll just get a small fine, all the way through having your car confiscated, or being arrested for reckless driving, or having what fines are out there is really across a very wide spectrum. And for our purposes, what exactly that is doesn't really matter so much. What I want to look at here is try to get an understanding of a kind of a qualitative understanding. So if we have a speed limit, let's say of 55 miles per hour, then as we go above that, if we push the limits, if we're speeding, then of course we run the risk of fines, of heavy fines, of arrest, of who knows what, losing your driver's license, and so on. That's kind of on the high side. On the other hand, if we're going low, if we're going too slow, our deliveries will be late, we lose competitive advantages, and so on. So that's where we are. So 55 in this case would be the sweet spot. Deviating from that to the left and right, or the high and low, is associated with risk for our business. So as we explore this domain a little bit further and go through the mechanics of speeding and being caught speeding, I should point out where we're talking about the American way of dealing with speeding. And for those of you who are calling in from abroad, you may know this from the movies, where the most common way of catching a speeding violation here in the US is that a police car measures your speed, goes after you, pulls you over, and then you get your ticket. That's the kind of situation we're talking about today. Now, when we think about managing risk in this context, I think it's a given that we know human drivers are always at risk of violating traffic rules, including speed limits. They don't even need to have any bad intentions. Just by being inattentive or who knows what, we may violate rules. And so here's one idea of how we can mitigate risk, and that is if we're operating a fleet of vehicles, like a fleet of trucks, we might think about equipping that vehicle fleet with radar detectors to reduce the risk of speeding violations. But for the purpose of this toy problem today, we're only looking at the risks of violating the law and its consequences, such as penalties, vehicle seizures, what have you. We're not talking about the accident risks related to speeding, which of course exist and are very, very important. Also, for the purposes of this example, we assume that radar detectors are legal, which is not the case in many jurisdictions. In fact, in many countries abroad, they're completely illegal. They're illegal in some states here in the US. And since you may not be familiar with them, let me just explain how they work. Radar detectors is a little black box that you put on your dashboard. And then as you drive, if there is a policeman somewhere hiding behind the bushes or behind the hill with a radar gun, then this radar detector can pick up on that radar signal from the policeman from a great distance, and therefore alert you that somebody is checking speeds. You can slow down and therefore not get caught speeding. Having said that, we by no means do want to advocate speedings or advocate the use of radar detectors. Speeding is dangerous, so don't get any ideas from this webinar. This is just an illustration, and we're using this topic simply because everybody knows all the variables involved. So let's get to our study questions, and there are several of them. One is, what is the base risk of getting caught speeding without a radar detector? How much can a radar detector reduce the risk of speeding violations? So what is the economic value of such devices to an organization? And we might ask, do they lead to any unintended consequences? So that's what we want to find out. And whenever we talk about risks and risk mitigation, it would be quite natural to think about data, about collecting data and analyzing and so on. But here in this particular situation that we are faced, unfortunately, we don't have any data. Yeah, and perhaps that is not surprising, because data about how police are trying to track down speeders, that's a closely guarded secret by them, because if we knew, then we would also know how to circumvent it. So it's quite obvious that to the public, there is practically no data about kind of the mechanisms of catching speeders. Now, if you go online, there are forums out there where a lot of people talk and share anecdotal evidence, but that's really not useful for our purposes. So what happens if we have no data? Well, there's this old saying, without data, you're just another person with an opinion. So if we're now considering we are running the business that is considering implementing the radar detectors, then I'm sure you have different viewpoints and different concerns. Perhaps the CFO may worry about cost, the general counsel may worry about liability, the VP of marketing may worry about customer satisfaction, and so on. Ultimately, the boss decides what needs to be done. So, but you can see how this could be quite an unsatisfactory situation, because you just have opinions clashing with each other. It's really very difficult to bring all those considerations into the same framework. That's where Bayesian networks come in. Once again, Bayesian networks come to the rescue, and I'm sharing with you this map of analytic modeling and reasoning, which you have probably seen before. The point of this graphic is to highlight that Bayesian networks can cover the entire spectrum of model purposes, and can also cover the entire spectrum of where models come from, cover the model source. And in particular, what is of interest today is reasoning without data, just working with theory without any data from any external source. So where does this theory come from? Well, even without data, humans do possess useful knowledge, qualitative or quantitative, tacit or explicit, about many aspects of the world. So, and in last week's webinar, we talked about two such problems. We talked about the white cab, yellow cab problem and the where is my bag problem. And we reasoned about all those problems, and we tried to resolve them just with domain knowledge without any data. But the key point there was, last week we only took the knowledge, if you will, of a single expert. We took kind of one consolidated view and encoded that into a Bayesian network with which we could then reason about the problem domain. So, but needless to say, individual opinions, the knowledge of individuals is full of biases. And we don't need to go through all of them. So just think of overconfidence, confirmation bias, framing effect, and so on. Many of these biases are described in detail in the book by Kahneman and Tversky, Judgment Under Uncertainty, Heuristics and Biases. This is a book I quote quite frequently because it really summarizes and lists many of those biases in great detail. So how can we overcome some of these individual biases? Well, one is to proceed to a group of experts instead of relying just on a single one. That's what we want to do today, or at least we want to simulate this process. But as it turns out, groups have biases too. And you will be familiar with groupthink, group polarization, and so on. So there's a whole new list of issues that we have to deal with when we work with a group of people who discuss a topic. So how can we overcome this? That's where the idea of the Delphi method comes in. That was developed in the 1930s and 40s by the RAND Corporation with the objective to develop a reliable opinion consensus of a group of experts. The idea was really to take the positive from groups, meaning that knowledge comes from a variety of sources, while preventing the negative, such as the groupthink and the polarization. How does the Delphi method do it? Well, in very, very briefly, basically it's an iterative procedure that elicits knowledge and assessments from experts via questionnaires, and then those questionnaires come back, they get consolidated, feedback is given to the experts, and then the process is repeated again. And the central idea in this Delphi method is that the opinions of individual experts will not become known to other experts. So you're really not constrained what others might think about what you say or what your thoughts are. So interestingly, the first application of this was on a topic where clearly little data was available. The objective was to estimate the military objectives of the Soviet Union during the Cold War. Other than through intelligence efforts, you would probably know fairly little about what exactly they're doing. So the idea was, let's kind of pretend to, let's kind of put us into their shoes and then think about what they would do. And the group of experts did that and came up with some fairly good assessments, as it could be verified many years later. So now you may say, really, is this a scientific approach? You know, because we're so conditioned to using data and statistics and so on. Well, our alternative is that we throw up our hands in despair, you know, and say, who knows? Or we can make the most of an admittedly unsatisfactory situation and try to obtain the relevant intuitive insights of experts. So that's what we want to do now. And what we've done is we have, if you will, modernized the Delphi method, or I should say, you probably have not heard much about the Delphi method because it wasn't really used a lot in recent decades. One of the reasons was it was tricky to implement just for logistical reasons, because of paper and pencil type questionnaires and multiple iterations. This was all not so easy to handle. So we have updated this approach and integrated it with Bayesian networks with BayesiaLab and created what we call the Bayesian Expert Knowledge Elicitation Environment, for short, BEAKY. This is what the workflow looks like. You start off with brainstorming and model construction. That is done in BayesiaLab, followed by knowledge elicitation, which happens through BEAKY. And then finally, the model that is elicited is then used for inference and optimization. So let me talk about this in a little bit more detail. So the first round, which we will soon do, or at least simulate, is the brainstorming and model construction part. You have a facilitator, you have a group of experts, and in that group you discuss the variables of interest, causal relationships, and together you create a qualitative network structure. So and once you have that, then the group disperses, and then we proceed to eliciting the quantities, the parameters of the network by querying all experts individually, separately from each other. Technically, this works by submitting the network to the B-key server, which then queries the experts individually. They can simply log in through a web interface and then answer questions related to this network. And through multiple iterations, you would then gradually elicit all the parameters and end up with a fully specified and estimated network, if you will, that can be used for inference. And that really brings us to the third part. Then you can jointly use this network for inference and optimization. That's what we want to do now. And I'm actually perfectly on time with my introduction. It is 1:20, so I think we're doing well on time. At this point, I'd like to leave PowerPoint. Just bear with me a moment as I'm making that switch, and go into BayesiaLab, where we will start to build a network of our domain. So I just need to move a few things around here, and then you should see BayesiaLab momentarily. Just bear with me. Okay, I hope you can now all see the BayesiaLab screen. I've just started the software, and I now want to encode our problem domain. I now want to think about, all the things we talked about: radar detectors, speeding, police. How does all that fit together? And how can we represent this in a Bayesian network that we can subsequently use for reasoning? So one by one, I will introduce variables and then see how they connect. And unfortunately, this will be a bit of a one-way street for us, since we're not all in the same room and we can't do this as a work group. So basically what you will hear is how I'm kind of thinking out loud as I'm building this network. So let me start off. I will start off with a very first node that I put here on my graph panel. And this is the node that will reflect the speed limit. Obviously a very important one here in this context. Now, by default, all new nodes at BayesiaLab are binary, which is not appropriate here. So I will open my node editor and create intervals for this node. So I'll turn this into a numerical variable. And here I'll say I want to look at speed limits between 30 and 80. And I want to have 5 intervals for that. So this is now kind of the domain for this particular node, speed limit. Okay. Now, just for context, what we're now going to look at, we're thinking of basically an hour on the road. We'll just think of an average time frame that we're traveling with our truck, with our van, and think about the probabilities in this context. So we have speed limit now, and a variable that will certainly or should certainly relate to that is my travel speed. And for this too, I will create intervals, but perhaps for this node, I need to create some further intervals because we can certainly exceed the speed limit. So I will create a range here from 30 to 100 in 7 intervals. So we now have that. And I would argue the travel speed, hold on, I need to complete the name here. Travel speed should certainly be related to the speed limit. So I'm drawing an arc, a qualitative arc, saying that speed limit is a cause of travel speed. And I think this can be easily accepted, because the other way, the arc wouldn't work. I can't say my speed changes or affects the speed limit. So that's variable number 2. And now let's think about what else belongs in here. Of course, police presence. That plays a major role, because if we had no concern about getting caught, then perhaps we would speed even more than we already do. So here's a variable, police presence, and that as a binary variable, true and false, makes perfect sense. So that works. Okay, so now we can think about, well, how do they interact, these variables? And we may perhaps say, perhaps between police presence and travel speed, we have a variable, let's call it traffic stop. So that represents whether or not the police kind of measures my speed and then stops me on that basis if I'm speeding. So, but there are a couple of things in between that we also need to consider. And most importantly, one of the questions we have is whether a radar detector would help us in this particular situation. So I'm now going to introduce a variable for radar detector, but that's not the usual shape that you're familiar with. Rather, this is not the round node, but here we have a box, a square, which means in BayesiaLab that this is a decision node. So what does this mean? A decision node is a node that we can utilize to evaluate policies as a function of probabilities and utilities. We will see in a moment what all that means. For now, I'll say, I will call this new node, this decision node, radar detector. And for the values of this, I'll just say off and on. Or I could say present, absent, or something like that. Here, I'll just keep it very simple. So here we have the radar detector. And it's quite obvious that what the radar detector is trying to do is to detect the police presence via a radar alert. So I'm encoding that. So this means whether or not there is a radar alert true and false, is a function of whether the police is present and whether the radar, and whether we have a radar detector or not. Importantly, as we will see shortly, that's not a deterministic node, because we'll see there are situations when the police is there and the radar detector doesn't go off, and conversely, we will have false alerts as well. Okay, so now how does this continue? Well, what happens if we do get a radar alert? I would argue if we get a radar alert, we will adjust our speed and potentially deviate from our original travel speed. So I'm creating a new node that's called measured speed. And for that, I will also create a range of intervals. Let's do 30 to 100 as before in 7 intervals. And now I will link radar alert and measured speed. So basically the reasoning is, if I get a signal from the radar detector, I will presumably slow down. To what speed will I slow down? Well, I would think we would probably slow down to what is the current speed limit. So in that sense, the the measured speed is dependent on my original travel speed and what the speed limit is. So now based on that measured speed, now this would be the criterion for pulling me over or not. Actually not quite, because I also need to consider the measured speed alone doesn't really mean anything. Rather, the question is, what is the speed delta versus the speed limit? That is really what is of interest, because that is what the police will utilize and determine whether it's worth pulling me over or not. For speed delta 2, I need to establish a range. And here I'm only interested really in the positive values, because if I have a negative speed delta, I can go as slow as I like. That's of no concern. So I will create here a speed delta from 0 to 50 miles per hour. Okay, and so the speed delta is a function of measured speed and speed limit. But what we need to realize here, whereas many of the other nodes we will subsequently have to elicit based on opinions, on assessments for lack of data, speed delta will be very easy to determine, because that is simply a function of measured speed and speed limit. So instead of trying to populate the conditional probability table, I can create an equation. In this case, a very, very simple equation that says measured speed minus speed limit. That is my function. It's like almost like an Excel formula that I can enter here. I validate, and with that I have now defined speed delta. I realize we haven't defined the other nodes yet, but that one is simply a function, a result of the others. There's not much judgment that has to go in there. Okay, next step. So how does speed delta relate to traffic stop? We don't know yet, but we know that that is obviously a function. And traffic stop obviously also has police presence as a prerequisite. Because I can speed, if nobody is there to catch me, then there won't be a traffic stop. Okay, let's continue, because ultimately this is what we're worried about. We're worried about getting a ticket and a fine. So let me just try to fit all, whoops, I didn't mean to, here we go. Just was trying to get it all onto the screen. So now once I'm stopped by the police, then I risk getting a ticket, and how bad the ticket is or how expensive it will become for me is clearly a function of the speed delta. So here, let me define the range for my ticket. So in here, let's say I'm creating a range from $0 to $1,000. I'm saying this is the range of my tickets. In fact, let me create a distinct category for $0, because we know sometimes you get pulled over and then you just get a warning when you get away with it. So for that, I've now just created a $0 state. All right. So yes, so this is basically just looking at getting caught. Let's now think about what utilities that brings about. Well, one utility, a negative utility, is certainly the ticket. That's what I want to avoid. And the way we can capture that in BayesiaLab in terms of evaluation is via utility nodes. So this is probably also a node that you may not have seen before. This is this diamond-shaped utility node, and that is what we use when we want BayesiaLab to evaluate one or multiple utilities with regard to establishing a policy. So I am now drawing an arc from ticket to the utility node. And here the utility node is very simple to define because I could use specific values. Here I'm once again using a formula. I'm saying the utility is the negative value of the ticket amount. So I'm just saying minus ticket. This is how BayesiaLab will now compute the utility, in our case, the negative utility of getting a ticket. So, but are there any positive elements in here? Well, we need to think about, we're in the transportation business. Perhaps we are compensated by the amount of miles we travel in a day. Or here, let's look at all this by the hour. We can now think about, well, what's the benefit of going a little bit faster? Here I would argue, let's say the speed limit is 65. If we go 70 and do that over an hour, then I travel 5 miles further than I would have otherwise. So if I get compensated, let's say $1 a mile, then I make $5 more in that hour. So there is a utility, not necessarily a legal utility, but nevertheless a potential benefit. So I'm now creating a new utility node that consists, or that is linked to, speed limit and travel speed. So here I'm saying, again using a formula, if my travel speed exceeds the speed limit, then that's positive. On the other hand, if I'm slower than what the speed limit allows, then that would be a -2. So it goes in both directions. So with that, I've defined this utility node. And now you may say, well, let's now elicit the probabilities. But we need to do one more thing, and that's what I alluded to earlier, saying, well, are there potentially any side effects or unintended consequences of using a radar detector? And I would say, yes, there could very well be, because if you give somebody a radar detector, they may feel safe driving faster. So that may actually affect their travel speed. So I'm now drawing an arc from radar detector to travel speed. And now we need to consider how the behavior changes of people who have a radar detector. It's not just that they will maintain their existing speed and will just prevent them from accidentally getting into a speed trap. Now they may kind of be a little bit more daring and go faster in the hope that they will basically get a warning before running into a policeman. So now the question becomes, we see all these little yellow warning triangles. This means the probabilities for these nodes, the marginal probabilities and the conditional probabilities, are all not yet defined. So if we had data, this would be beautiful, because then we would just associate our database and click parameter estimation, and we would have all that. But here we only have our opinions, perhaps some anecdotal evidence, some personal experience, and that's what we now need to work with. That's as good as it gets. And perhaps if we have a reasonably large group of experts, we can perhaps bring together a fairly solid amount of knowledge and encode this in the Bayesian network. So how do we go about this? In the previous webinar, we just went straight into the individual nodes and typed in our probabilities. Now what we want to do is use the Bayesian expert knowledge elicitation environment. So let me show you how this works. I have prepared a network for that, just for the elicitation purposes. I've added a few more things and fine-tuned things and cleaned things up. In particular, one thing I forgot, and I will talk about this later, is this value node. I forgot to add it in the earlier network, but let's postpone that. So what I want to elicit now are two nodes in particular, the first one being speed limit. And there I would ask people, like, what is the distribution of speed limits as you travel? Like, how much time do you spend at each speed level, or at what is over the course of an hour, how many different speed limits do you encounter, and how long do you drive at 70 miles an hour or 80 miles an hour, and so on. So we want to elicit probabilities for these individual states. As I said, I could just type something in here. There are some values that are already put in. But what we now want to do is send this as a question to our experts. And we can do this in BayesiaLab by clicking Assess. Or let me actually go a step back and show you how we can set up our experts. Here in our case, I've now just opened up the expert editor. I've defined 5 experts that have been invited to participate in this session. Now, these are all dummy records. At the moment, these are not real persons, but just dummy accounts. But I could include all kinds of information. I could include images of the individuals, comments, etc. That's what I would define here. Okay, from here I can open an elicitation session. Basically, I could prompt BayesiaLab, or I could prompt the BKey server from BayesiaLab to start an elicitation session, which now enables me to submit questions to my experts. So let me do that now. I'll say I want to elicit these probabilities. I click Assess, and in the assessment editor, I can now request a BKey elicitation. So now this sends the requests, the elicitation requests, to all my experts. So let me now share with you, let me basically share the screen of one of these experts to see what that would look like. Just bear with me. Now I need to switch to a different, or I need to switch the presenter to different computer. Hopefully this works. Make presenter. Okay, I think that works. So I'm now inside the view, the expert view, where I'm now given basically a form that allows me to fill in my beliefs. You see these sliders here. I can now set what I think the distribution is of speed limits. I could also type in specific values. I can say this is 17%, and I can provide my own confidence level. So because there may be questions that I'm quite familiar with, where I can, with great confidence, say, I know this, I learned this in school, or for other things, I may say, I'm not really entirely sure. So I set validate. This sends the response back to BayesiaLab. So let me now go back into BayesiaLab. I will not share that with you because I don't want to switch back and forth all that often. I will now submit a second question, and that is about the radar alert. I now want to get the judgment of people about the false positives and the true positives of a radar detector. So again, I will submit an assessment task. And as soon as I submit that, it appears on the web page of the expert, who can then provide what he believes as to what the false, here in this case, at the top of the page, we see the context. It says radar detector on, police presence false. Now the question is, how many false alerts do we get? And for those who have ever experienced radar detectors, they actually have, there are lots of false positives. I have one, I don't really use it. I thought I would use it, but there are just way too many false positives to make it useful. So I've now set the false positive rate, and now I'm setting the true positive rate. So let's say 9 out of 10 times, make sure you just type that in, 9 out of 10 times, the radar detector catches a police, or catches the police presence, and I'm also, let's say I'm actually very confident in that assessment. I set my confidence to 95. I click validate. So I've now submitted 2 responses to elicitation tasks, and now I will switch back to my principal computer. So bear with me again as I'm making that switch. Okay, so here you now see how the responses came in. I've only simulated a single expert here, so you see that out of the 5, only 1 has indeed responded. And so I'm now collecting that information, click accept, OK, and with that I have now populated the conditional probability table of radar alert and speed limit. As you can imagine, there are many more that would have to be elicited, and where we probably have to think quite a bit harder about, well, how does what are those probabilities? This one perhaps being the most interesting one. How would I change my travel speed if I had a radar detector? So that really requires the judgment, getting the judgment from all the experts to come up with some quantities in this regard. Okay, we don't have time to go through all these probabilities, so I will do it like the chefs on TV, where they prepare a dish, put it in the oven, and 1 second later pull out the finished product. That's what I'm going to do here now. I'm proceeding to a fully specified or fully estimated Bayesian network that was elicited using the Bayesian expert knowledge. Now I shall just say BKey. It's such a mouthful. That's why the abbreviation comes in very handy. So here's my final network. I have opened this up in validation mode, which shows me all the monitors of all the nodes. And I can see the distributions of my travel speed, the distribution of speed limits, the associated distribution of measured speeds, the speed delta, and so on. So we can now read all the probabilities. And let me now do one thing. Let me erase what I had originally entered here and start from scratch. Now I want to use this network to help me determine, is it prudent to use a radar detector? Basically, do I get a greater value for the organization having it on versus having it off? Knowing well that there are multiple paths of influence. On the one hand, the radar detector alerts me. On the other hand, the radar detector also may incentivize people to speed. So what is the net benefit? I don't really know, but taking all my utilities, I can now make a policy decision with BayesiaLab. The way it works is I'm simply selecting learn static policy. Now watch the radar detector, the blue box here, and see what happens, which state is selected as a result of learning the static policy. It was so quick, you probably barely noticed it, but now you saw that the radar detector, the selected policy state switched to on. So BayesiaLab determined we have a higher utility with the radar detector installed and on as opposed to off. Let's simulate this. In the purple boxes, you can see the summary values. Let me just toggle back and forth between off and on. So radar detector off, I have a total utility of minus roughly 2.5. With the radar detector on, I'm at a total utility of roughly 6.8. So it means the utility for my organization is greater, even though when you look at the travel speeds and even the measured speeds, they are higher. Now, of course, whether the effect is positive or negative really all depends on the knowledge that I have elicited from my experts, from my stakeholders. So, and there it now becomes very obvious that these assessments may take multiple iterations because once you see how this works, then you may realize, oh, hold on, I didn't consider this dynamic, or a certain relationship may be missing, let's introduce that. So you can see how this might be an iterative process. But beyond that, I have here another node. I call it the value node. I'm wiggling it around here that I failed to introduce when I drew up the network earlier on. I just wanted to show how we can introduce additional nodes, so I can perhaps beyond just computing specific states on and off, I can now perhaps look at, well, how does the value to my organization change as a function of speed if I have my radar detector? So if I had the radar detector, how fast should I go? What is the kind of the critical limit to minimize or to maximize the utility for my company? Or conversely, if I don't have a radar detector, how fast can I safely go? And again, maximize the utility for my organization. So let's do that. Let's perhaps start with radar detector off. The value node in this case is simply, it's just a summary of the utility nodes. So the two individual utility nodes, if you sum them up, they would give you the value of this target node that I have created here. Just another way of representing it. And very often in BayesiaLab, you can do similar things with different methods. I could have used function nodes, for instance, and so on. There are multiple ways of dealing with this. So what I want to know now, I have set radar detector to off, and now I want to see how my travel speed affects the value to my organization. I select travel speed and now run a target mean analysis with standard effects. And here is what we get. So this is with radar detector off. And assuming the given distribution of speed limits, I can basically say here up to a certain point, perhaps 60, 65, my utility is at a plateau. And after that, not surprisingly, I run into the risk of getting caught speeding and the fines pile up and so on. So my expected value goes down. That's perhaps fairly straightforward. Let's now do the same thing with the radar detector on and see how that affects the situation. Analysis, visual, target, posterior mean, standard. And here is my curve. So now it looks a little bit different. And I can now see how I'm also pushed a little bit further to the right. So and this is intuitive. Given that I have the radar detector, I can go a bit faster. But still, as I go beyond a certain threshold, as I go beyond 70, 75, even the radar protector won't really protect me sufficiently to run into the adverse effects of getting caught speeding. So those are the things we can now analyze. We can experiment with different utilities, time savings, and depending on the context, I may have different values that I put on time or distance gained and so on. But I wanted to show this to you how we can now reason about a problem domain, even though we have no data. We've just elicited knowledge from different stakeholders and experts. And of course, this model is only as good as their thinking, their collective thinking. But what you will find is that their collective thinking often comes together into a very robust model that is useful and intuitive, that is also readily interpretable by external stakeholders. So once perhaps a work group creates such a network and estimates the parameters from expert knowledge, you can then take this to the executives and they will probably be able to relate to this reasoning, or the general counsel can look at this and say, okay, how did you go about quantifying this risk? And what is the risk going from this speed threshold to that level and so on? All these things can now be answered. And then of course, if you were to implement that, if you were to set up your fleet with the radar detectors, then perhaps over time you could collect data and fine-tune your estimations, or rather replace your original expert knowledge elicitation values with actual data. Here's just one final thought. I think we have a few more minutes. Let me just illustrate how, because you may say, what, couldn't we have done this in Excel? Couldn't we have, just put together a spreadsheet? Well, for two reasons, the answer is no. First of all, in an Excel spreadsheet, you can only work with single point values. Here we have distributions. We have a distribution of speeds. We have probabilities. We don't have, or we only have a few deterministic relationships. Many relationships are probabilistic. So those are the things that would be very difficult to encode in a spreadsheet. Another thing what we can do here, whereas we have reasoned from cause to effect, from travel speed to ticket, from travel speed to value, what we need to bear in mind, we can also reason in the opposite direction. So perhaps if one of your employees gets a ticket and is trying to argue that it wasn't really such a big deal and he wasn't really going so fast, if you take the model, you could say, okay, I set a ticket. Where's my ticket here? Here we go. Let's say the employee gets a $50 ticket. We can now reason backwards and say, well, what travel speed did he probably go? If he had a radar detector, got a $50 ticket, what is our expectation how fast he went? And here in this case, we can reason back from ticket all the way to travel speed and so on. So this now allows us to reason backwards and forwards and thus familiarize ourselves with this model. And this may also give us ideas how we can improve it further. So with that, let me switch back to PowerPoint for a few concluding remarks. Just bear with me as I'm switching my sharing again. Always requires quite a few clicks to get from PowerPoint back to, or rather from BayesiaLab back to PowerPoint. Just bear with me. And I should also mention I have quite a lot of screenshots from all the steps that we have done. I have screenshots in the slides that you will be able to download later. So let me wrap things up. Please don't forget we have a user forum. That's where we can have discussions about webinars, about features, about all issues related to BayesiaLab. This is also where we will post comments and carry on a conversation with you about any questions that may arise from this webinar. Now, if this made you interested in BayesiaLab or Biki, you can learn all about our technology, our software, its pricing, its licensing options on our website. We have a detailed pricing and licensing guide. And of course, you can try this out yourself, what we just went through. You can go through exactly the same reasoning. You can't do the elicitation part, but you can encode your own assumptions, your own beliefs into a Bayesian network and then reason with it and experiment with it. Our webinar series continues next week. That's Friday, March 16th. At that time, we will talk about optimizing health policies with Bayesian networks. Should also be a very interesting topic. For March 23rd, we don't have a topic yet. We also encourage all our webinar participants, if you have some interesting ideas for a webinar, a problem domain that you think would lend itself for presentation, for discussion in a webinar, please let us know. We would certainly like to consider that. And I must not fail to mention our course program. It continues in April in Sydney, Australia. Fabulous destination, so you may want to consider that. Many other opportunities. I should also let you know that we have another course coming up in San Francisco, July 23 through 25th, 23rd through 25th, at a great venue right downtown San Francisco, and you may wish to consider that. And of course, please put our annual conference in your calendar. This will be in Chicago this year, November 1st and 2nd. We have a great venue right downtown Chicago off Michigan Avenue. We expect great speakers from all over the world, so it would be great if you could join us. Well, with that, I would like to thank you very much for your time and interest this afternoon. I would love to carry on the conversation. Please feel free to reach out, send questions directly to my email, or connect with us on Twitter, Facebook, LinkedIn. We'd very much like to keep talking with you and explore additional problem domains. And with that, once again, thank you. Have a great weekend and drive safely.